Welcome to a lesson with Dr. Powell. Let's take a look at Prim's algorithm, which is an algorithm that finds a minimal spanning tree on an undirected weighted graph where each of the edges has a weight. Okay, so to do this algorithm, what we do is we start with a vertex. And from that vertex, we find one of the minimal edge weights that touch that vertex. So we could pick either this one or this one. Let's just pick this one. All right. Now we have two vertices that we check edges from, but we don't choose the edge we've already used. We've already chosen. So we've chosen that one. Okay, so let's pick out, so between these, we notice this one is the minimum one. Okay, now we have three vertices, and we get to look at this edge, that edge, that edge, and that edge. So we need to choose either this one or this one. We can choose either one. Why don't we choose this one? All right. Now from these, but we're not going to choose edges we've already used. We're not going to choose edges that we've already used. So we go and we look at these ones, and we notice this one. And as soon as we have 1, 2, 3, 4 edges, because we have, so which is one less than the number of vertices, we're through. So that is what Prim's algorithm is. Next, let's look at the complexity of Prim's algorithm. So we could look at maybe the adjacency matrix of the algorithm, the adjacency matrix of the graph, and looking at this, we could look at the column of the first vertex that we're considering. So we go down that column, and we'll see some ones in there. Now those ones will represent edges that are adjacent that we can check. So maybe to begin with, we could even go down all the columns and take the edges that are represented in each column and sort them. So sorting each column would be, well, each column has maybe, if there's n vertices, it would be n log n. Since there's n columns, you're already at n squared log n. So just by sorting each column. Now, as we use an edge, then we look at the row right here, and wherever we see a 1, wherever we see a 1, that's another edge that we want to merge in. It's just, in fact, it's the same thing as taking the corresponding column that's associated with this guy. So if this is in the second position, we take the second column, and that's going to be the same since this is undirected graph, so it's a symmetric matrix. Either a row or column will be the same. So we could look at the corresponding column, if we will, and each of those will correspond to some edges. And let's put those into our list, merge sort them. And so whenever we come to an edge, if we haven't included that particular column, we'll merge it in at that point. That way, as we're going, our list of edges to consider will only be ones that are adjacent to, or edges that actually touch in to what we've already used, so that at each step it can be connected. So this particular algorithm maintains connectivity as we go throughout. Now, as we're doing this, we keep everything sorted, and so we have a running list, and we use what's minimum in that list. And as soon as we use it, we use it and we merge if we need to. We get rid of it, or so we use it, we get rid of it, that particular edge. Then we sort, and then after we sort, then we pick the next minimum. Then if we need to merge sort, then after we use it, we do a merge sort, and then we find the new minimum. Now, sometimes we won't need to find merge sort. Often we won't. So we'll just kind of keep on going through and getting our and then we can just go and always use the minimum here. At least, I mean, there's the potential of needing to merge or not needing to merge. Okay, but essentially that's kind of how we go about in that particular process of Prim's algorithm. So the complexity of, well, first of all, we sort each column, then we need to merge sort, and we need to traverse through the list of edges. So the list of edges is O(n) squared, which is trumped by just sorting all the columns. So really, the complexity so far of just sorting the columns is n squared log n. But then we're going to merge sort. Now that's where, at least in this particular implementation, which I'm describing, has worse complexity than this. So to merge sort, what we're doing is we're going to be having n-1 merges, and each time we're merging, well, let's see, the first time you merge a list of length n, another list of length n. Then you merge a list of length n with a list of length 2n. Well, potentially it might be smaller, but so we're overestimating completely here. And then we have 3n and n and so forth. And you add all these up, there's going to be n-1 ways of adding that up. So, or of this particular thing adding. So you're going to have n-1 from all these n's. And then you're going to add to that the sum of all these guys, which is n times the sum of 1 through n-1. And the formula for that actually is, so 1 through n-1 is n times n-1 all over 2. And if you work through this is a cubic polynomial. So we're looking at O(n) cubed as the complexity, at least in this calculation of complexity, I suppose, of this implementation. Thanks for watching.